Now that we know about the one-time pad, let's talk about making the one-time pad more practical using something called the stream cipher. But before we do that, let's do a quick review of where we were. So let me just remind you that a cipher is defined over a triple of sets called a key space, a message space, and a ciphertext space. And a cipher is a pair of efficient algorithms called E and D. E stands for encryption and D stands for decryption. And the only property that we need to satisfy is that decryption is the opposite of encryption. In other words, if I encrypt a message M using a particular key and I decrypt using the same key, I get back the original message. Last time we looked at a couple of weak ciphers like the substitution cipher and the Vigenère cipher. We showed that all of them can be easily broken, so you should never ever use those ciphers. Those were just for historical reference. And then we looked at our first example of a good cipher, namely the one-time pad. Let me just remind you how the one-time pad is defined. Basically, the message space is the set of all n-bit strings. The ciphertext is a set of all n-bit strings, and similarly, the key is the set of all n-bit strings. And the way we encrypt is by a simple XOR. To encrypt the message, we just XOR the message and the key. That gives us the ciphertext. And then to decrypt the ciphertext, we just do this XOR again, and it's easy to show by properties of XOR that in fact decryption is the opposite of encryption. And then we talked about this lemma. In fact, we proved it. That says that the one-time pad has perfect secrecy, which means that if you're just an eavesdropper and you just get to see a single ciphertext, you're not going to be able to deduce any information about the encrypted plaintext. Unfortunately, we also said that Shannon proved this lemma. We called it the bad news lemma. That basically says that any cipher that has perfect secrecy must have really long keys. In other words, the key length must be at least as long as the length of the message, which means that the cipher is not particularly useful, because if two parties have a way to agree on really long keys that are as long as the message, they, in some sense, might as well use that mechanism to already transmit the message itself. So in this lecture, we're going to take the idea of the one-time pad and try to make it into a practical encryption scheme. So this is what's called a stream cipher. So the idea in a stream cipher is rather than using a totally random key, we're actually going to use a pseudo-random key. And to explain how that works, I need to define what is a pseudo-random generator, a PRG. So a PRG, really, all it is just a function, and I'll call it G for generator, that takes a seed. So I'm going to use 0, 1 to the s to denote all strings of length s. So this we'll call the seed space. So it takes an s-bit seed and maps it into a much larger string, which we'll denote by 0, 1 to the n. And the property is that n must be much larger than s. So in other words, we take a seed that might be maybe only 128 bits, and we expand it into a much larger output string that could be gigabytes long. That's what the pseudo-random generator does. And of course, the goal is that, first of all, the generator is efficiently computable. So the function g, there should be some sort of an efficient algorithm that computes it. So efficiently computable by a deterministic algorithm. It's important to understand that the function g itself has no more randomness in it. It's totally deterministic. The only thing that's random here is the random seed that's given as input to the function g. And the other property, of course, is that the output should look random. And the question is, what does it mean to look random? And that's something that we'll define later on in the lecture. Okay, so suppose we have such a generator. How do we use that to build a stream cipher? Well, the idea is that we're going to use the seed as our key. So our short seed is going to be the secret key. And then we're going to use the generator to basically expand the seed into a much larger random-looking sequence, or pseudo-random sequence, as it's known. So this would be g of k. And then we are going to XOR it just like in the one-time pad. We're going to XOR the pseudo-random sequence with the message, and that's going to give us the ciphertext. Or if we want to write this in math, we'll write C equals the encryption of the message M with a key K, which is simply defined as M XOR G of K. And then when we want to decrypt, basically we do exactly the same thing. It's basically the ciphertext XOR G of K, just like in the one-time pad, except that instead of XORing with K, we XOR with the output of the generator applied to K. So the first question to ask is, why is this secure? So basically, we only have one notion of security so far, which we called perfect secrecy. And so let's just quickly ask, can a stream cipher have perfect secrecy? Remember, in the stream cipher, the key is much, much shorter than the message. And so nevertheless, can it have perfect secrecy? So I hope everybody said the answer is no. The key is much shorter than the message. And we said that in a perfectly secure cipher, the key must be as long as the message. And therefore, it's not possible that a stream cipher actually has perfect secrecy. So the question is then, well, why is it secure? First of all, we would need a different definition of security to argue that the stream cipher is secure. And in particular, the security property is going to depend on the specific generator that we used. So in fact, the definition of privacy that we'll need to argue security of stream ciphers we'll see in the next lecture. But for now, let me show you one particular property that a generator must have, a minimal property needed for security. This property is called unpredictability. So let's just suppose for 1 second that in fact a stream cipher is predictable. So what does that mean? Suppose the PRG is predictable. What that means is essentially that there is some I such that if I give you the first I bits of the output, this notation bar 1 to I means look at the first I bits of the output of the function. Okay, so I give you the first I bits of the stream. There is some sort of an algorithm, there's an efficient algorithm that will compute the rest of the stream. Okay, so given the first I bits, you can compute the remainder of the bits. I claim that if this is the case, then the stream cipher would not be secure. So let's see why. Well, suppose an attacker actually intercepts a particular ciphertext, let's call it C. Right, so if this is the case, then in fact we have a problem. Because suppose that just by some prior knowledge, the attacker actually knows that the initial part of the message happens to be some known value. For example, you know that in the mail protocol, SMTP, the standard send mail protocol used in the internet, you know that every message starts with a word from colon. Well, that would be a prefix that the adversary knows that the message must begin with, from colon. What it could do is it could XOR the ciphertext with the words from colon, with the little prefix of the message that it actually knows, and what that would give it is a prefix of the pseudo-random sequence. So now it would learn as a result of this, it would learn a prefix of the pseudo-random sequence. But then we know that once it has a prefix of the pseudo-random sequence, it can predict the remainder of the pseudo-random sequence, and that would allow it to then predict the rest of the message M. Okay, so for example, if the pseudo-random generator was predictable given 5 bits of the pad, then every email encrypted using a stream cipher would be decryptable because, again, the attacker knows the prefix of the message, from which he deduces a prefix of the pad, which then allows him to compute the rest of the pad, which then allows him to recover the entire plaintext. Okay, so this is an example that shows that, in fact, if a PRG is predictable, then already there are security problems because a small prefix would reveal the entire message. As it turns out, even if I could just predict 1 bit of the output, even if given the first I bits, I can predict the next bit, the I plus first bit, already this is a problem because that would say that given, again, the first couple of letters in a message, I can decrypt essentially and recover the next bit of the message or the next letter of the message and so on. So this predictability property shows that if we use a PRG that's going to be used in a stream cipher, it had better be unpredictable. So what does it mean that a PRG is unpredictable? So let's define more precisely what it means for a PRG to be unpredictable. Well, first we'll define more precisely what it means for a PRG to be predictable. So we say that G is predictable if there exists an efficient algorithm, let's call it A, and there is some position, there's a position I between 1 and n minus 1, such that if we look at the probability over a random key, probability that if I generate a random key, and remember this notation means choose a random key from the set K, so this arrow with R just means choose a random key from the set K. Basically, if I give this algorithm the prefix of the output, so I give it the first I bits of the output, the probability that it's able to predict the next bit of the output, this probability is greater than half plus epsilon for some non-negligible epsilon. And non-negligible, for example, would be epsilon, which is greater than 1 over 2 to the 30. 1 over a billion, for example, we would consider non-negligible. So these terms, negligible and non-negligible, will come back at the end of the lecture and define them more precisely. But for now, let's just stick with the intuitive notion of what non-negligible means. And so this is what it means for an algorithm, for a generator to be predictable. Basically, there's some algorithm that is able to predict the I plus first bit, even the initial prefix. Okay? And then we say that an algorithm, that a PRG is unpredictable if, in fact, well, if it doesn't satisfy the property that we just defined. In other words, it is not predictable. But what does it mean more precisely for it not to be predictable? It means that, in fact, for all positions, for all I, there's no efficient adversary, no efficient algorithm A that can predict the I plus first bit with non-negligible probability epsilon. Okay? And this has to be true for all I. So no matter which prefix I give you, you're not going to be able to predict the next bit that follows the prefix. Okay, so let's look at some examples. Here's a silly example. Suppose I give you a generator and I ask you, is it predictable? Well, this generator happens to have the property that if I XOR all the bits of the output, I always happen to get 1. Okay, so I XOR all the bits, bit number 1, XOR bit number 2, XOR bit number 3. If I XOR all those bits, I happen to get 1. The question is that a predictable generator? And again, I hope everybody answered yes, that essentially, given the first n minus 1 bits of the output, I can predict the nth bit because it would just be the bit that's needed to make the XOR of all the bits be 1. In other words, if I give you all but 1 of the bits of the generator, you can actually predict the last bit of the generator. Now that we've seen that PRGs have to be unpredictable, I just want to mention a couple of weak PRGs that should never ever be used for crypto. This is a very common mistake, and I just want to make sure none of you guys make this mistake. So a very common PRG that should actually never be used for crypto is called a linear congruential generator. So let me explain what a linear congruential generator is. Basically, it has parameters. It has 3 parameters. I'll call them A, B, and P. A and B are just integers, and P is a prime. And the generator is defined as follows. Essentially, I'll say R0 is the seed of the generator. And then the way you generate randomness is basically you iteratively run through the following steps. You compute A times R of I minus 1 plus B modulo P. Then you output a few bits of the current state, output few bits of Ri. Then, of course, you increment I, and you iterate this again and again and again. Okay, so you can see how this generator proceeds. It starts with a particular seed. At every step, there is this linear transformation that's being applied to the seed, and then you output a few bits of the current state, and then you do that again and again and again and again. Unfortunately, even though this generator has good statistical properties in the sense that, for example, the number of zeros it outputs is likely going to be similar to the number of ones and so on. You can actually argue all sorts of nice statistical properties about this. Nevertheless, it is a very easy generator to predict, and in fact should never ever be used. In fact, just given a few output samples, it's easy to predict the remainder of the sequence. And as a result, this generator should never ever be used. Another example is a random number generator that's very closely related to the linear congruential generator. This is a random number generator implemented in glibc, very common library, that you can see. I just wrote down the definition here. You can see that it basically outputs a few bits at every iteration, and it just does this simple linear transformation at every step. Again, this is a very easy generator to predict and should never ever be used for crypto. And so kind of the lesson I want to just emphasize here is never ever use the function, the built-in glibc function random for crypto, because it doesn't produce cryptographic randomness in the sense that it's easy to predict. And in fact, systems like Kerberos version 4 have used random and have been bitten by that. So please don't make that mistake yourself. We'll talk about how to do secure random number generation actually in the next lecture. Before we conclude this lecture, I just want to give a little bit more detail about these concepts of negligible and non-negligible values. So different communities in crypto actually define these concepts differently. For practitioners, basically the terms negligible and non-negligible are just particular scalars that are used in the definition. So for example, a practitioner would say that if a value is more than 1 over a billion, 1 over 2 to the 30, we say that the value is non-negligible. The reason that's so is because if you happen to use a key, for example, for encrypting a gigabyte of data is about 2 to the 30, or maybe even 2 to the 32 bytes, then an event that happens with probability 1 over 2 to the 30 will likely happen after about a gigabyte of data. So since a gigabyte of data is within reason for a particular key, this event is likely to happen. Therefore, 1 over 2 to the 30 is non-negligible. On the other hand, we'll say that 1 over 2 to the 80, which is much, much, much smaller, is an event that happens with this probability is an event that's actually not going to happen over the life of the key, and therefore we'll say that that's a negligible event. As it turns out, these practical definitions of negligible and non-negligible are quite problematic, and we'll see examples of why they're problematic later on. So in fact, in the more rigorous theory of cryptography, the definition of negligible and non-negligible are somewhat different. And in fact, when we talk about the probability of events, we don't talk about these probabilities as scalars, but rather we talk about them as functions of a security parameter. So let me explain what that means. So these functions are essentially functions that output positive real values, or non-negative real values that are supposedly probabilities, but they're functions that act on non-negative integers. Okay, so what does it mean for a function to be non-negligible? What it means is that the function is bigger than some polynomial infinitely often. In other words, for infinitely many values, the function is bigger than some 1 over polynomial. Okay, so I wrote the exact definition here, and we'll see an example in just a minute. Okay, so if something is often bigger than 1 over a polynomial, we'll say that it's not negligible. However, if something is smaller than all polynomials, then we'll say that it's negligible. So what this says here is basically for any degree polynomial, for all d, there exists some lower bound lambda d such that for all lambda bigger than this lambda d, the function is smaller than 1 over the polynomial. Okay, so all this says is that the function is negligible if it's less than all polynomial fractions. In other words, it's less than 1 over lambda d for sufficiently large lambda. So let's look at some examples, and we'll see applications of these negligible and non-negligible concepts later on, but I just wanted to make it clear that this is how you would rigorously define these concepts. Basically, either smaller than 1 over poly or bigger than 1 over poly. One would be negligible, the other would be non-negligible. So let's look at some examples. So for example, a function that drops exponentially in lambda clearly would be negligible because for any constant d, there is a sufficiently large lambda such that 1 over 2 to the lambda is less than 1 over lambda to the d. Okay, so this is clearly less than all polynomials. However, the function, say 1 over lambda to 1,000, right? This is a function that grows very, very, very slowly. It barely ever moves. Nevertheless, this function is non-negligible because if I set d to be 10,000, then clearly this function is bigger than 1 over lambda to the 10,000. And so this function is bigger than some polynomial fraction. Now let's look at a confusing example, just to be tricky. What do you think? Suppose I have a function that for odd lambda happens to be exponentially small, for even lambda happens to be polynomially small. Is this a negligible or non-negligible function? Well, by our definition, this would be a non-negligible function. And the intuition is if a function happens to be only polynomially small very often, that actually means that this event, an event that happens with this probability, is already too large to be used in a real crypto system. Okay, so the main points to remember here are that these terms basically correspond to less than polynomial or more than polynomial. But throughout the course, we'll mostly use negligible to mean less than an exponential, and non-negligible to mean less than 1 over a polynomial. So now we saw the core idea for converting the one-time pad into a practical cipher, namely a stream cipher. And then in the next lecture, we're going to see how to actually argue that the stream cipher is actually secure. That's going to require a new definition of security. since perfect secrecy is not good enough here, and we will see that in the next lecture.